This video deals with a series of definitions and technical terms fundamental to understand the language of thermodynamics. Some of these terms are already in our everyday vocabulary as a result of the broad-based use of thermodynamics concepts in everyday life. It was popular among the 19th century scientists to coin technical terms using Greek or Latin words instead of English. Consequently, many of the key terms or words in thermodynamics are really Greek or Latin words, which in the 21st century are properly foreign to you. But when these terms are translated into English, you will find that their English meaning is identical to their thermodynamics use. For example, the English translation of the term isothermal is simply constant temperature, which is the physical meaning of what the term isothermal is meant to imply. Though this may seem like a small point to you at this stage, your understanding and ease with this subject are greatly enhanced if you pay particular attention to the English meanings of these otherwise meaningless technical terms. The name thermodynamics itself is an example of a Greek technical term. Basically, it means the process of converting heat into mechanical power. Modern thermodynamics deal with more than just thermal energy. Today, thermodynamics deal with the laws that govern the transformation of energy from one form to another. There are four basic laws of thermodynamics: the zeroth, first, second, and third laws. Like all of the other basic laws of physics, each of these laws is generalization of observed events in the real world, and their discovery was the result of an individual perception of how nature functions. Curiously, the order in which the thermodynamics laws are named does not correspond to the order of their discovery. The zeroth law is attributed to Fowler and Guggenheim in 1939, the first law to Joule, Mayer, and Kolding in about 1845, the second law to Carnot in 1824, and the third law to Nernst in 1907. The first and second laws are the most pragmatic and consequently the most important to engineers. A thermodynamics analysis involves applying the laws of thermodynamics to a thermodynamic system. The thermodynamic system often is referred to as just a system, and its boundary is defined simply as its surface. The system and its boundary are always chosen by the analyst, which is you. They are almost never specified in a problem statement. It should be clear that if different systems are used to analyze the same quantity, they should produce the same result in each case. A system does not have to be fixed in space. It can move, deform, and increase or decrease in size with time. Basically, there are three types of systems: isolated, closed, and open. Here you see a pan of water, which is in a mass and energy in a previous insulated box, thus forming an isolated system. Here we have a closed system, wherein the content of the pan are closed by an airtight lid, but heat energy enters the pan from the burner. And here, water, which is mass, enters the pan by crossing the system boundaries. So here the pan is an open system. Notice that whether a system is open or closed depends on how the analyst views the system. Here, the system could be made a closed system if the system boundary is extended to include the faucet. All the water pipe going back to the water treatment plant, for example, and the water supply for the plant. But such a system will be too large to analyze properly, since we must be able to find all the energy that crosses its boundary at any point along the boundary. Therefore, it is much easier to view this as an open system with a small, well-defined system boundary. In the end, the choices of the proper system, along with the proper form of thermodynamics law, always are decisions that you, the analyst, must make whenever beginning to solve a thermodynamics problem. Therefore, making a sketch of the system that shows the system boundary is a useful aid in making these decisions. The system sketch in thermodynamics is equivalent to the free body diagram sketch in mechanics, and its value cannot be overstated.